So we're going to cover some materials and probability here between now and the start of the second semester. These are some notes, these are some problems that I thought might give you some hard time, plus I want you to read these chapters. I also know that some of you don't, so I'm going to hit some of the highlights. So a sample space is an action deals with theoretical probability, and you might have looked at this a little bit in earlier years. We want to list the actual possible outcomes. So some of these are pretty easy to do. Sometimes you'll want to do a tree diagram to help yourself out. And I'm for choice A here. Let's look at this. So I'm flipping my first coin. I could either get heads or I could get tails. Then I'm flipping a second coin. And again, the second coin could be heads, tails, heads, tails. So if we list all those outcomes, heads, 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 tails, tails, heads, and tails, tails. See what I'm doing is I'm just tracing out the tree diagram. Okay? You might have done, if you think back to high school biology, you made Punnett squares, same math. In AP Bio, you get into much more complicated Punnett squares. But you can do the same kind of thing. I'm just matching up the rows and the columns. Okay, see, I get the same list of outcomes. So this is the sample space of flipping two coins. If you had three coins, well, you could do a 3 by 3 Punnett square. I don't quite remember how to do that. I could just add another branch here and list that, so that would be okay. Now, are these equally likely? Well, there's a 25% chance that I'll get each one of these outcomes. Okay, so that's true. Now, if you're just talking about one head or one tail, well, that's a half, and those are all just one of each. So that's a different question. Okay, so how about the family is 3 children, record the number of boys? Well, we could certainly make a tree diagram, and I'm not saying it's always the best way to go, and in fact, this case, I don't think it is, because I could just list them. I could have 0 boys, I could have 1 boy, or I could have 2 boys, or I could have 3 boys. So that's my sample space. Now, are those equally likely to happen? I decided to make a tree diagram to answer this question about equally likely, and so I wrote each. So here is the first child, here's the second child, here's the third child, and all I'm doing is I'm tracing out these paths and writing down how many boys are there, and then we're going to see if they're equally likely. And I'm already seeing that probably not. 2 boys, there's 1 boy, there's 1 boy, and there's 0 boys. So I'm seeing right now that there's only one way to get all 3 boys out of 1, 2, 3, 4, 5, 6, 7, 8. So 1 out of 8 versus there's 3 out of 8 ways to get 2 boys, 3 out of 8 ways to get 1 boy, and 1 out of 8 ways to get 0 boys, which so are they equally likely? No, they are not. So for part C, flip a coin until you get a head or 3 consecutive tails. Well, I could flip a coin once, have heads, done. Then what if I have to flip it again? Well, that would mean I had to get a tail on the first flip, a head on the second, done. So what if that didn't happen? Well, I'd have a tail on the first flip, tail on the second flip, then I could get a head on the third flip. Lastly, tail, tail, tail. So that's the result of getting 3 consecutive tails. So are these equally likely to happen? Well, there's a 50% chance, or the probability of me getting heads would be 0.5. And then for this one, then that looks like that baby situation, right? Remember where there's the Punnett square we could think about maybe, and how that was, there was a 50% chance of getting 1 of each when there's 2, so that's the same. However, with this one, this is back to that thing about boy-girl, and remember you scroll back and look at my tree diagram a minute ago, there was 3 ways to get two, what it was, boys and girls. So there's 3 ways out of 8 to get 2 boys or 1 boy, and there was 0 or 1 way to get 0 boys or 1 way to get 3 boys. And this is that same situation. So even though these first 2 are the same probability, this kills it. And we know there's only 1 out of 8 ways for that. So these are not equally likely. Okay, so for the sample space for rolling 2 die and recording the larger number, well, there's the numbers 1 through 6. It's possible I could roll 2 die and get 2 ones or snake eyes. It's possible that I could roll 2 die and get 2 sixes or boxcars, but those aren't likely to happen. So just in that situation right there, I know that these are not equally likely. More ways to roll a 2 than there are to roll just 2 ones. Okay, so that's sample spaces, and I hope that helps you answer that question. So the law of large numbers versus the law of averages. There's no law of averages, folks. People say that we're due for something. That's a fictitious thing that we as humans make up. The law of large numbers says the more and more times that you repeat an event, you're going to approach theoretical values. So if I buy a scratch ticket and I win, I got lucky. If I keep buying scratch tickets, I'm going to end up losing a lot more often than I'm going to win. It isn't that the law of averages was telling me, well, hey, I bought 5 scratch tickets in a row, and I've lost all of them. Chances are I'm due to win the next one. Well, that's the law of averages, and that's what gets people in trouble. We'll look at an example or 2. You'll see them. Okay, so I pulled these right out of the book. So the weather forecaster makes a prediction that there's going to be a 25% chance of rain. Well, what he's doing is he's talking about the long-term average, or the long-term probability of what happens when the weather's like this on that day, based on these conditions. It's not a law of average thing. This is the law of large numbers. So that means in the long run, it's going to, with the conditions we have today, it could rain 25% of the time. Now, this cold streak thing. The batter failed to get a hit in 7 consecutive times at bat, and then hits a home run. He said, well, he was due. Well, as long as each swing or each time at bat is independent of the previous one, we can say that there's no such thing as this being due for a hit. Now, there are other issues that can go on, but then that's not a probability situation. Okay? So, I highly recommend that you go watch this video. I'll have it linked in the homework on the course website, but this is a short 10-minute against all odds video. Talks about casinos. There's an interview with a casino owner. It's in there. I think it's worth your time. So I'll let you read this problem, and then you can stop the video and come back and listen to what I'm saying about it. So what's going to happen is, because the Excalibur has so many people going through their casino, and most of them lose, they're going to make enough money to cover that one player that's going to win that $3.9 million jackpot. Okay. So why would the spokesperson from the machine, the slot machine, want to make that statement? Because they want to have people come in and gamble in that casino. Okay, so if they get the people thinking, oh, I might win on playing that game, well then they'll want to advertise that, even though in the long run the people coming in will lose their shirt, and the casino owner will make a ton of money. So some probability rules from the textbook that I hope you read. A probability has to be between 0 and 1. It can be 0, it can also be 1, and anything in between. But it can't be more than 1 or less than 0. It can't be negative. And the sum of all the outcomes in an event has to have a sum of 1. So if we look at these possibilities, so for this distribution A, we can talk about, well, there's a 25% chance of yellow, red, 25% chance of yellow, green, and blue. So all of these numbers are between 0 and 1. And if we add those up, they add up to 1. So that is a legitimate probability assignment. So let's look at B. All of those are between 0 and 1, so that's good. If we find the sum of these, let's see, those two add to 70, and another 30 makes it 1. So again, that is a legitimate probability assignment. Now if we look at this next one, those add to, so they're all between 0 and 1 first off, so that's good. But if we add these up, we'll get more. We get 50 here and 50 there. We're already at 1, so this is not a legitimate probability assignment because the sum of them is greater than 1. In this case, 0 and 1, so it's okay there, and if we add up those numbers is 1, so that again is a legitimate probability assignment. This one here, we can see a negative probability, and we can see a probability that's greater than 1, so that's out. Okay, so I hope that's pretty easy. I just want to make sure you point it out to you. So one thing when you're working with probability, it's sometimes handy to make a table, and this problem asks us to do that. So we've got Facebook users. The Facebook reports 70% of the users are outside, so that means they'd be inside also. There's some people that are inside the United States. And 50% of its users log on to Facebook every day. Suppose that 20% of the users are U.S. citizens who log on, or U.S. Residents that log on every day. So make a probability table. So we've got everyday people and not everyday. We've got inside the U.S. We've got outside the U.S. And we've got our totals. And I'll write a total down here. And I'll put some rows to help keep myself organized. Okay, so we know it's 100% the total. We know that 70% of its users are outside the U.S., so there's 70% outside, which would mean there'd be 30% inside, right? Because those two rows have to add up to 100, or 1. Let's see what else. Then suppose that 20% of its users are U.S. users that log in every day. So I know that every day inside, that's 20. And I know that 50% of the users log on every day, so that's 50% of the users log on every day, so that must mean 30% are outside. And so now to get the rest of this information filled in, we know that 10% of the people, if 20% of their users log on every day, and there's 30 that live inside the U.S. log on every day, and there's 30% overall, that leaves that to be 10, and that would have to be 40 there, and that would have to be 50% there. And if we check our arithmetic, that adds up to 50, that adds up to 50, that adds up to 30, that adds up to 70, so we're good. There's my probability table. Now I can answer some questions about this, but that's not for this problem. We've got some probability rules that I'm going to introduce to you and link some words to them. So one of the things, when you're reading a problem and they ask, what's the probability, and it contains an or sometimes they'll word it such that you got to think about, oh, well, this is just an or question. That means you're going to add two probabilities. So the probability, and this is in case you've never seen this before, this U means or. Okay. So, and this upside down U means and. And you see that down here in this multiplication rule has this and. So we're going to talk about, you're going to look at some problems and get some practice with it. So if two probabilities or two events are independent of each other. That means one doesn't affect the other. All you got to do is add the two probabilities. Now, if it so happens that they both can't happen at the same time, they're disjoint. This book it also uses the word mutually exclusive. If they can't both happen at the same time, this doesn't exist because the probability of that happening is 0. If they do happen and can happen at the same time, well, then we're going to subtract it. So it's an important idea. Independence means two events don't affect the other. That doesn't mean disjoint or mutually exclusive events are not independent. It means one affects the other. So keep that in mind. When you're reading a problem and it says find the probability of this in that happening, or both happening at the same time, that's going to be a multiplication probability. And again, if they're independent, you really don't have to worry about this weird notation. We're going to look at some where you do, but really just going to multiply them. Now, this probability of not happening, that's a complement. I need to write. So that's a complement. They're complementary events, just like complementary angles. Let's see if I can spell this right. Complementary. I'm running out of space. So what that means is, in our book that talks about the probability of some event's complement, they'll put like a little superscript, like a little exponent c. And the way you do that is you take 1 minus the probability of the event happening. And we'll look at plenty of examples. Now, this probability of at least 1, you're going to find the probability of none and take that away from 1. And that'll always be the way you deal with these at least 1 kind of problems. Okay, so find the probability of not happening, and then you subtract that from 1. You find the complement of it. Okay, let's look at some examples. So let's apply some of these rules now in this problem. So we've got 5 landlines. The probability of having no landline is 0.25. So that means the complement of that would be the probability if they have a landline, which would be 1 minus 0.25, which would be 0.75. So what's the probability that at least all 5 of them have a landline? Well, the probability for the first person, or the first phone number, is 0.75. Now, we're going to assume these are independent, that one phone not being a landline is independent of the next one. So 0.75 again for the second one, and then we could do it again, 0.75 by the third, and for the fourth, and then the fifth. But the easy way to write this is 0.75 raised to the 5th power. So on your calculator, you can do that. You can do 0.75, if you've got a grapher, 0.75 caret 5. I'm getting 0.237 if I go to 3 decimal places. Okay? What's the probability? What's the probability that at least one, so there's that buzzword, at least one of them does not have a landline. So we're going to find the probability that they all have a landline. So we know there's a 75% probability that any one house has a landline. We're going to raise that to the 5th power, which we just did there. But now we're going to subtract that from 1. We'll subtract that from 1 because that'll be the probability that at least 1 does not, or 2 does not, or 3, or all of them even. So if we'll do that, and that will be our answer. I won't bother calculating that. So that's at least 1 does not have a landline. And then C, what's the probability that at least one of them does have a landline? So stop this video, think about it for a minute, come back and see how I'm doing. So at least one of them does have a landline. Well, we want to find the probability that none do. No landlines. So that's the probability for any one of them not having a landline is 0.25. So we're going to raise that to the 5th power. So 0.25 to the 5th is a very small number. I want you to understand that my calculator is telling me 9.765 e to the negative 4. Well, that means we're moving the decimal point over 4 places to the left, that's a pretty small number. So the probability of them, at least one of them having a landline, is going to be pretty darn close to 1, because 1 minus that almost 0 number is going to be close to 1. The calculator is telling me that it's 0.999 to 3 decimal places. Okay, so ask yourself, when you're dealing with these at least one problems, ask yourself the opposite of that. Find that probability, take it away from 1. So we're going to put all this together. Let's see. So I've got 20% yellows, 20% reds, and then orange, green, or orange, blue, and green were 10. So the rest are brown. So if I add up these probabilities, well, that's 20 for the yellows, 0.2. The probability of red was another 0.2. The probability of orange was 0.1. Probability of a blue was 0.1. Probability of a green was 0.1. Well, we know that these probabilities have to have a sum of 1. So we add that up. What's that? 4, 5, 6, 7. So that tells me 30% of the M&Ms were brown. That's supposed to be a 30. Here, let me erase that and rewrite that a little better. Okay, so what's the probability that a random M&M is brown? 0.3. If it's yellow or orange, notice the or word, so that tells me I'm going to add some. And I also know that an M&M can't be both yellow and orange, so this is okay just to add the two probabilities. So yellow and orange would be 0.3, because 0.2 plus 0.1. Not green, well, that's a complement. I know the probability of an M&M being green was 0.1, so 1 minus 0.1 would be 0.9. And back at this time, there were no striped M&Ms, so the probability of that happening is 0. So now for B, now we're doing multiples, and we have a large number of M&Ms, so we're not worried about anything being dependent. We'll assume that taking an M&M out doesn't change the overall probabilities, because there's so many M&Ms it doesn't matter. So all brown. Well, for each M&M, we know that it's a probability of 30% being brown, so I'm just going to raise 0.3 to the third power because I'm picking out 3 M&Ms. For question 2, the third one is the first one that's red. So let's see. The probability that the first one is not red is going to be, well, 1 minus 0.2 is 0.8. So that's the probability of not being red. And then the next one we also don't want it to be red, was 0.8. Then the last one we want it red, so that's 0.2. So if we do 0.8 times 0.8 times 0.2, that will be the probability for choice 2, answer question 2. None are yellow. Well, again, we know the yellows are, there's 20% of them are yellows, so 1 minus 20% is, or 100 minus 20% is 80 or 0.8. Now we're in at least 1 green. So we know the probability of it being green is 0.1. So let's find the probability of it not being green. Would be 0.9, and we're drawing 3 of them, so the probability that all 3 are not green would be 0.9 to the third power. Now, to get the at least 1, we're going to subtract that answer, and that would be the answer for choice 4. So now we're getting into the situation where these are not disjoint problems, or they're not mutually exclusive, because people could own both a cat and a dog. In fact, they tell us that. So there's a couple of ways to deal with this. You could do straight with a rule. So the probability of somebody owning a dog is 0.25. The probability of somebody owning a cat is 0.29. And we're going to subtract the probability of them owning both a cat and a dog. And if we do that, what is that? 20, that's 54 minus 12 is, what, 42? So 42%. Now, sometimes you're reading a problem and it just doesn't make any sense to you. So make a picture is always a good thing. And one good picture we can make is a Venn diagram. So we know that 12% of the people own both cats and dogs. So that intersection in the middle is 0.12. We know that 25% of the people own the dog, but 12% of them own a cat also. So we're going to subtract 12 from 25, and I'm going to get the 0.13. For the cat, same kind of deal. 29% have a cat, but 12% of them already own a dog also. So we're going to subtract 12 from 29 and make that be what, 0.17? So at this point, you can see if you just add up these three numbers, we're going to get 0.42, which is what the addition rule said, and it'll take away. It's already by subtracting the 12%, you don't count it twice, and that's what the important part here is. Okay. So this is a conditional probability problem, and it deals with an and, because we want to know the probability the person likes to watch football and that they like to watch basketball. So because these are not independent events, somebody could like, in fact they tell us we can see that there's 27 people that like both football and basketball. These are not disjoint problems, so we got to deal with this this other probability here. We can't just multiply the two probabilities. And with the table, it's really easy because we can actually see that. If we do some totals here, if we add, let's see, so that's 50, so that should be 65 here. This would be 35 here. If we add up those probabilities, we get 100. And it'll probably be the same way this going across the top. What's that? 40. And that would be 60, and that adds to 100. So there's my totals. That checks. So what's the probability that a person likes to watch football, given that they also likes to watch basketball? Well, it's 27 out of 100, or 27%.